Look up at the night sky, and you're looking back in time. Every star, every wisp of galaxy, every faint flicker of light began with a story written in the very first moments of our universe, a story written not in words, but in molecules. Long before planets took shape, before stars ignited, before atoms even knew how to come together, something profound and delicate was happening in the newborn cosmos. In the searing heat just after the Big Bang, the first chemical bonds were forming. These weren't just any molecules, they were the universe's very first handshake, the initial building blocks that would one day lead to worlds, life, and us. What were they? How did they arise from a formless sea of energy? And why does their existence shape everything we see around us today? We often picture the early universe as a place of chaos, pure energy, expanding at an incomprehensible rate. But within that storm, order was already beginning to emerge. In the cooling aftermath of creation, simple atoms like hydrogen and helium drifted through the darkness. Yet for chemistry to truly begin, these atoms had to find each other, to bond. The first molecules were humble, nothing like the complex structures we see in nature today. But their formation marked a turning point. They were the seed from which all complexity would eventually grow, the spark that lit the path toward stars, nebulae, and the rich chemistry that makes our universe so astonishingly diverse. This is where our journey begins. We're about to explore 30 captivating theories scientists have put forward to explain how those earliest molecules came to be. Some ideas are elegant, others wildly speculative, but each offers a glimpse into a chapter of cosmic history that's still being decoded. From the subtle influence of dark matter to the role of ancient radiation, from the echoes of the Big Bang to the possibilities of universes beyond our own, this is a mystery that challenges our understanding of physics, time, and existence itself. So settle in, let's travel back to the beginning and uncover the secrets of the molecules that started it all. In the beginning, there was hydrogen. As the universe expanded and cooled from its initial fiery state, a monumental shift occurred, a period scientists call recombination. For hundreds of thousands of years, the cosmos was too hot for atoms to exist. It was just a thick, opaque fog of free protons and electrons buzzing with raw energy. But around 380,000 years after the Big Bang, the temperature finally dropped enough for these particles to slow down and capture one another, forming the very first neutral atoms. This was the moment the cosmic fog cleared, allowing light to travel freely for the first time, the light we now detect as the cosmic microwave background. Yet, for the story of chemistry to truly begin, these lone hydrogen atoms had to find a partner. The formation of the first molecule, molecular hydrogen, was a far more delicate process. Two hydrogen atoms floating in the vast emptiness of space faced a problem. When they collide, they tend to just bounce off each other unless there's a way to shed the excess energy of their encounter. The solution came in the form of a rare three-body reaction, where two hydrogen atoms meet while a third particle, often another atom or a free electron, is present to carry away that extra energy, allowing a stable bond to form. It was a slow, inefficient process in the early universe's sparse environment, but it was enough. These fragile H2 molecules began to appear, the universe's first tentative steps into chemistry. Their impact, however, was anything but tentative. Molecular hydrogen played a role far greater than simply being first. It acted as the universe's first coolant. Atomic hydrogen isn't very efficient at radiating away heat, but molecular hydrogen, with its more complex structure, is exceptionally good at it. As these early clouds of gas, seeded with the first molecules, began to lose their thermal energy through this cooling, they could no longer support themselves against their own gravity. This cooling allowed vast, diffuse clouds to collapse inward, growing denser and hotter at their cores until the pressure and temperature ignited the first nuclear furnaces, the very first stars. Without those first, simple hydrogen molecules, the cosmos might have remained a dark, sterile expanse of scattered gas, forever waiting for a spark. While molecular hydrogen set the stage for the first stars, there is an even more ancient contender for the title of the very first molecule, one that formed in a universe still screaming with the heat of its own creation. This brings us to the helium hydride ion, known as He+. Picture the universe just seconds after the Big Bang. It is an unimaginably dense, hot plasma, a seething soup of nuclei and electrons. At this point, temperatures are still too high for complete atoms to exist, let alone form stable bonds. But as the cosmos expands and cools, protons, which are simply hydrogen nuclei, begin to mingle with the next most abundant element, helium. The crucial moment arrives when a lone helium nucleus captures a free electron. This single act doesn't create a neutral atom, but rather a unique ionized form of helium that is primed for a reaction. Now, this ionized helium atom, still buzzing with energy, encounters a lone proton, a hydrogen nucleus. In that brief encounter, the two particles share their electrical charge, bonding to form the helium hydride ion. This is not a molecule in the way we usually think of it. It's a molecular ion, a charged and fragile thing. But in the harsh environment of the infant universe, this fleeting combination represents a monumental breakthrough, the first time two different atomic nuclei came together in a stable bond. For decades, this was purely a theoretical idea, a prediction of our chemical models of the early cosmos. Scientists could run the calculations, but the question remained, did it actually happen, and could we ever find proof? That proof finally arrived in 2019, not from the edge of time, but from a place much closer to home, a planetary nebula called NGC 7027. Using a sophisticated instrument aboard the Sophia Airborne Observatory, astronomers detected the unique infrared signature of the helium hydride ion. This discovery was monumental. It confirmed that this exotic molecule can and does form in nature, existing in present-day environments that mimic the extreme conditions of the early universe. Finding it in a modern nebula was like discovering a living fossil, a creature from a bygone era that had somehow survived into the present day. It validated a key prediction about the chemical dawn of the cosmos. Yet, the ultimate prize remains out of reach. The real holy grail for cosmologists is to detect the helium hydride ion in the deep, ancient universe from that primordial era when it was the only molecule in existence. Such a discovery would be like finding the first footprint on a deserted beach, direct evidence of the universe's very first chemical step. It would open a new window into the conditions of the infant cosmos, allowing us to test our models of how everything began with unprecedented precision. The hunt continues, with powerful telescopes scanning the most distant, ancient regions of space, hoping to catch an echo of that first, simple bond that started it all. But while helium hydride may have been the very first, it wasn't necessarily the most influential player in the cosmic drama that followed. This brings us to another, often overlooked contender in the story of our chemical origins, lithium hydride. After the Big Bang, the universe wasn't just a sea of hydrogen and helium. Trace amounts of a few other light elements were also forged in that initial fiery crucible. Among them was lithium, specifically the isotope lithium-7. In the grand scheme of things, there wasn't much of it, only about one lithium atom for every 10 billion atoms of hydrogen. But in the vast emptiness of the early cosmos, even a tiny amount can have an outsized effect. The theory suggests that as the universe continued to cool and expand, these scarce lithium atoms encountered the abundant hydrogen. Under the right conditions, a lithium atom could share its single outer electron with a hydrogen atom, forming a stable molecule of lithium hydride. The process for its formation was likely even more complex and rare than that of molecular hydrogen, requiring very specific energy conditions. Yet, if it did form, lithium hydride could have played a unique and crucial role. Its chemical properties are fascinating. It's an ionic compound, meaning it doesn't just share electrons like hydrogen molecules do, but actually transfers them, creating a much stronger and more polar bond. This polarity would have made it an incredibly efficient coolant. Imagine those first collapsing clouds of gas that would eventually form the very first stars. Molecular hydrogen was doing a decent job of radiating heat away, allowing the cloud to contract. But lithium hydride, with its different molecular structure, could have acted as a supercoolant, working in tandem with hydrogen to accelerate the cooling process in certain regions. This might have triggered the collapse of smaller, denser clumps of gas much faster than previously thought, potentially leading to the formation of the universe's very first population of stars in a different way. It's a theory that adds a new layer of nuance to our models of star formation, suggesting that trace chemistry, not just gravity, dictated the pace of cosmic evolution. The challenge, and the reason this hypothesis remains so compelling yet difficult to prove, lies in detection. The spectral signature of lithium hydride is incredibly faint, a whisper of a signal that has been stretched and diluted by 14 billion years of the universe's expansion. Our current telescopes simply aren't sensitive enough to pick out this specific fingerprint from the cosmic background noise at such immense distances. However, the next generation of observatories, like the James Webb Space Telescope and other planned extremely large telescopes, are being designed with this exact kind of detective work in mind. Astronomers are actively modeling what the lithium hydride signature should look like, creating a treasure map for these powerful instruments. Finding that signal would be like discovering the chemical catalyst that helped ignite the cosmic dawn, confirming that even the most minuscule ingredients in the primordial soup had a vital part to play. But if the formation of the first molecules was so difficult in the vast, empty expanse of the early universe, how did they ever manage to become abundant enough to trigger the birth of stars? This puzzle leads us to one of the more exotic and fascinating theories, one that invites a mysterious and invisible player onto the stage: dark matter. We know this enigmatic substance makes up the vast majority of the matter in the universe, a gravitational scaffold around which the visible cosmos is built. But what if dark matter did more than just provide gravity? What if it actively helped to build the universe by serving as a catalyst for chemistry itself? In the conventional model, the first molecules formed slowly through rare three-body collisions in a near-perfect vacuum. It was an inefficient process. But this theory proposes an alternative pathway, suggesting that certain types of hypothetical dark matter particles could have provided the very surfaces needed for hydrogen atoms to meet and bond. Imagine two hydrogen atoms drifting through the primordial darkness. In empty space, their chance of forming a stable molecule is incredibly slim. But if they were to both encounter a large, cold dark matter particle, that particle could act like a tiny grain of dust, absorbing the excess energy from their collision and allowing them to stick together as molecular hydrogen. In essence, a dark matter particle would function as a catalyst, enabling a reaction that would otherwise be almost impossible. This isn't just a wild guess, it's grounded in specific models of what dark matter could be. One prominent candidate is a class of particles known as macros, or macroscopic dark matter. Unlike the tiny, weakly interacting particles often theorized, macros could be much larger, perhaps even asteroid-sized conglomerates of exotic matter. Another candidate could be a form of charged dark matter, particles that interact not only through gravity but also through a type of dark electromagnetism. If such particles existed in the early universe, they would have been far more effective at facilitating chemical reactions than the sparse, free electrons were. They would have provided countless microscopic platforms, dramatically accelerating the production of molecular hydrogen. The implications of this are profound. If dark matter catalyzed the formation of the first molecules, it would mean that the invisible 85% of matter in the universe didn't just build the gravitational wells for galaxies to form. It actively supplied the fuel for the very first stars to ignite within them. This theory elegantly solves the problem of how enough molecular hydrogen accumulated to begin the process of cosmic structure formation so quickly after the Big Bang. It paints a picture of a universe where the visible and the dark are inextricably linked from the very first chemical handshake, collaborators in the construction of everything we see today. Of course, this remains a highly speculative idea. We have yet to directly detect any form of dark matter, let alone confirm that some types could have these specific catalytic properties. Proving it would require not only identifying dark matter, but also understanding its detailed interaction with ordinary matter in those first moments. Yet, that is the power of such theories. They push the boundaries of our imagination and provide new, testable ideas for how the cosmos might have woven itself together from the fabric of the unknown. While dark matter offers one exotic pathway for molecule formation, another theory invites us to consider the most extreme gravitational engines in the cosmos: black holes. But not the colossal ones we find at the centers of galaxies today. This idea focuses on a hypothetical first generation known as primordial black holes. These wouldn't have formed from dying stars. The universe was far too young for that. Instead, theorists propose they could have been born from the wild fluctuations in density that occurred in the very first fraction of a second after the Big Bang. Imagine tiny, incredibly dense knots of spacetime, some perhaps no more massive than an asteroid, scattered throughout the expanding cosmos like seeds. If they existed, their presence would have radically altered the environment for early chemistry. The influence of a primordial black hole would be twofold, driven by its two most famous properties: immense gravity and Hawking radiation. First, consider its gravitational pull. In the sparse early universe where atoms were spread incredibly thin, a primordial black hole would act like a powerful cosmic magnet. It would draw in a steady stream of the surrounding hydrogen and helium gas, creating a localized cloud of much higher density around it. This alone would be a game changer. The rate of chemical reactions depends heavily on density. The more particles you pack into a space, the more often they collide. Around one of these black holes, the chances of two hydrogen atoms meeting and forming a molecule would skyrocket compared to the near-perfect vacuum of intergalactic space. It would become a tiny, hyper-efficient factory for molecular hydrogen, but the story gets even more interesting when we factor in Hawking radiation. This is the theoretical process by which black holes slowly lose mass and energy, emitting particles back out into space. For a very small primordial black hole, this radiation wouldn't be a faint whisper, it would be a significant outflow of energy, effectively heating the immediate surrounding area. You might think that heat would prevent molecules from forming, and for a region very close to the black hole, that would likely be true. But a little further out, this energy could create a unique Goldilocks zone. The combination of intense gravity pulling material in and Hawking radiation pushing energy out could stir the gas, creating turbulent, dynamic conditions perfect for triggering complex reactions. It would be a cosmic crucible far hotter and more active than the cold, placid regions elsewhere. This theory suggests that the first complex chemistry in the universe may not have happened uniformly across the vast emptiness. Instead, it could have occurred in brilliant, isolated flashes around these exotic objects. Each primordial black hole would have been the heart of a tiny, violent ecosystem, potentially jump-starting the production of molecules on a local scale long before the first stars ever began to glow. If this were the case, the cosmic dawn may not have been a single, synchronized event, but rather a staggered awakening, with the first lights flickering to life in the dense atmospheres of these primordial anomalies. Their eventual evaporation through Hawking radiation would then have scattered these molecular building blocks back into the universe, seeding the cosmos for the next stage of its evolution. While definitive evidence for these ancient objects remains elusive, their potential role offers a captivating alternative narrative for how our molecular universe began not with a slow simmer, but with a series of intense, localized fires. To truly grasp the origins of the first molecules, we must journey back even further to a time before atoms, before nuclei, to an event so brief and violent it set the entire cosmic stage: inflation. This wasn't just a rapid expansion, it was a period of exponential growth that happened in a fraction of a second, smoothing out the universe and stretching it to an enormous size. But according to quantum theory, perfect smoothness is impossible. Even in that hyper-accelerated void, tiny quantum fluctuations were inevitable microscopic ripples in the fabric of spacetime itself. As inflation blew up the universe, it magnified these infinitesimal ripples into vast hills and valleys of density, the fundamental seeds from which all future structure would grow. This is the profound connection. The distribution of galaxies we see today, and even the very first molecules, can be traced back to these quantum whispers amplified by inflation. This theory proposes that the pattern of these primordial density fluctuations didn't just dictate where galaxies would cluster billions of years later. They directly controlled the environment for the very first chemistry. Think of those density variations as a cosmic blueprint. In the regions that inflation designated as slightly denser, there was simply more stuff, more hydrogen, more helium, more of every primordial particle. After recombination, when the first atoms formed, these overdense regions had a head start. With particles packed more closely together, the probability of a successful collision skyrocketed. The rare three-body reactions needed to form molecular hydrogen weren't quite so rare there. These patches became the most efficient nurseries for the universe's first molecules, creating localized pockets rich with the molecular fuel needed for cooling and collapse. Conversely, the underdense regions, the valleys in the cosmic landscape, were destined for a different fate. Here, matter was spread incredibly thin. The average distance between a hydrogen atom and its nearest neighbor was vast, making the chance of a bonding collision astronomically low, almost to the point of impossibility. In these voids, the formation of molecular hydrogen would have been stifled, dramatically delayed, or perhaps even prevented altogether. This theory suggests that the first chemical activity in the universe was not a uniform event but a patchwork, a direct reflection of the blueprint laid down by inflation. The first bonds formed precisely where the ancient quantum dice had rolled in favor of density. The implications of this are staggering. It means that the largest structures we observe, the great cosmic web of galaxies and filaments, and the smallest, the first fragile hydrogen molecules, are intimately connected, sharing a common origin in those first fleeting moments. The pattern of the cosmic microwave background radiation, which is a snapshot of the universe just 400,000 years after the Big Bang, shows these exact density variations. The hot and cold spots on that map are the imprints of inflation's quantum seeds. This theory posits that if we could map the distribution of the very first molecular hydrogen clouds at the dawn of time, that map would perfectly align with the hot spots in the CMB. The first chemistry was simply the next step in a chain of events that began when the universe was less than a trillionth of a second old. This idea elevates the formation of the first molecules from a local chemical process to a cosmic inevitability, a predetermined outcome written into the fundamental code of the universe. It wasn't random chance that determined where the first stars would ignite. It was the echo of quantum noise from the beginning of time, guiding the formation of the molecules that would make star formation possible. This provides a beautifully elegant and deeply unified narrative, linking the quantum world to the cosmic scale through the simple, elegant handshake of two hydrogen atoms. This brings us to a deeper, more nuanced layer of the story, one that involves a heavier, rarer cousin of the common hydrogen atom, deuterium. In the first few minutes after the Big Bang, as protons and neutrons fused to form the first atomic nuclei, most of the neutrons were captured to create helium-4. But a tiny, precious fraction of them, only about 1 for every 100,000 protons, ended up paired with a single proton, forming the nucleus of deuterium or heavy hydrogen. This isotope is chemically almost identical to regular hydrogen, but its nucleus contains both a proton and a neutron, making it twice as heavy. And that minute difference in mass would have profound consequences for the early chemistry of the cosmos. Theorists suggest that as the first atoms began to mingle, these rare deuterium atoms wouldn't have just been passive bystanders, they would have been highly sought-after partners. When a deuterium atom encounters a regular hydrogen atom, they can bond to form a molecule called hydrogen deuteride, or HD. While this might seem like a minor variant of molecular hydrogen, its formation was actually far more efficient in the cold, sparse environment of the early universe. The reason lies in the subtle physics of their interaction. Because a deuterium atom has a slightly different distribution of its internal charge, it creates a stronger permanent dipole moment. This makes it much more effective at radiating away the excess energy from a collision, allowing an HD molecule to form through a simpler two-body process rather than requiring a rare three-body encounter. It was, in a sense, a more robust and reliable handshake. The impact of this efficiency was immense. Even though deuterium was thousands of times less abundant than regular hydrogen, hydrogen deuteride molecules could have formed at a comparable, or perhaps even greater, rate than simple H2 molecules in certain regions. And HD is a superstar when it comes to cooling. Its enhanced dipole moment means it can radiate thermal energy away far more effectively than its lighter cousin. In those primordial gas clouds that were on the verge of collapse, the presence of even a small amount of HD could have dramatically accelerated the cooling process. It would have acted like a supercharger for star formation, enabling smaller, colder clumps of gas to condense and potentially leading to a different population of the very first stars, smaller, dimmer, and longer lasting than the behemoths we typically imagine. But the deuterium story doesn't end there. An even more exotic molecule could have played a role, molecular deuterium, or D2, where two deuterium atoms bond together. The chances of this happening were incredibly slim, given the extreme rarity of deuterium atoms. For two of them to find each other in the vast emptiness would have been a truly exceptional event. Yet, in the densest knots of the primordial gas, it's not entirely out of the question. And if it did form, D2 would have been the ultimate coolant of the early universe, its efficiency far surpassing even that of HD. Its presence could have created ultra-cold pockets within the gas, micro-environments where conditions were perfect for triggering the very first gravitational collapses. Beyond their role as cooling agents, these deuterated molecules hold another, perhaps even more valuable, key for cosmologists. They serve as exquisite tracers or cosmic barometers for measuring the density of ordinary matter, what scientists call the baryon density in the early universe. The amount of deuterium created during Big Bang nucleosynthesis is exquisitely sensitive to this density. If the early universe was packed with more protons and neutrons, more collisions would have occurred, and nearly all the deuterium would have been fused away into helium. A lower density would have allowed more deuterium to survive. Therefore, by measuring the primordial abundance of deuterium, we can precisely determine the baryon density of the young cosmos. This is where molecules like HD become crucial. While we can estimate deuterium abundance from the absorption lines of distant quasars, looking for the spectral signatures of HD in the most ancient astrophysical objects provides a powerful independent check. It's a direct probe of chemistry that was seeded by that primordial nucleosynthesis. By studying these molecular fossils, we are essentially taking a core sample of the universe's composition from a time before the first stars polluted it with heavier elements. This allows us to test the fundamental predictions of the Big Bang model with remarkable precision, confirming that our understanding of the universe's first few minutes is indeed on the right track. The humble deuterium atom and the molecules it formed thus provides a critical bridge between the nuclear physics of the Big Bang and the chemical dawn that followed. When we talk about the first stars, we're entering a realm of cosmic giants. These weren't like the stars we see today. They were behemoths known to astronomers as population 3 stars. Theorized to be hundreds of times more massive than our Sun, they lived fast, burned furious, and died young in spectacular supernova that first seeded the universe with heavy elements. But these titans couldn't just form out of nothing. Their birth required a specific set of conditions, and at the heart of it all was a critical problem of physics: how to shed heat. This is where the story of the first molecules becomes the story of the first starlight. In the primordial universe, the only ingredients available were hydrogen, helium, and a trace amount of lithium. A cloud of this pure, simple gas might want to collapse under its own gravity, but it faces a formidable opponent: heat and pressure. As a gas cloud collapses, it heats up, and this increased thermal pressure pushes back against the force of gravity, effectively halting the collapse. For a star to be born, the cloud must find a way to cool down, to radiate that thermal energy away into space, allowing it to continue condensing into an ever denser, ever hotter core. Atomic hydrogen, the most abundant substance, is notoriously bad at this. It's inefficient at radiating away its energy, especially at the relatively low temperatures of those early gas clouds. The universe needed a better radiator. This was the pivotal role of molecular hydrogen. Its formation, though slow and difficult, was the key that unlocked star formation. Unlike a single atom, a molecule has more ways to vibrate and rotate. These internal motions allow it to emit photons of light at specific wavelengths, effectively acting as a release valve for the cloud's built-up thermal energy. As these early clouds, seeded with their first H2 molecules, began to cool, they lost the internal pressure that was holding them up. This allowed gravity to win, pulling the cloud inward in a runaway process of collapse. The core would heat up to millions of degrees, finally triggering nuclear fusion and igniting the first stellar furnace. Without molecular hydrogen's cooling power, the universe might have remained a dark, sterile place forever. But the narrative of population 3 star formation isn't as simple as just adding H2. For a long time, models suggested that this cooling process would only work efficiently for very large clouds of gas, leading to the formation of exclusively supermassive stars. This created a puzzle. While we have strong theoretical reasons to believe these giants existed, our understanding of star formation today suggests a range of sizes. Was the first generation of stars really a monochromatic population of behemoths? A compelling theory suggests otherwise, introducing a more efficient coolant that could have allowed for a greater diversity in the first stars: hydrogen deuteride, or HD. HD is the molecule formed when a hydrogen atom bonds with an atom of deuterium, heavy hydrogen. While it might seem like a minor variant, its cooling properties are dramatically superior. The reason lies in its asymmetry. A regular H2 molecule is symmetric, both ends are identical. This symmetry means it has no permanent electric dipole moment. HD, however, is asymmetric. The deuterium atom, with its extra neutron, creates a slight imbalance in the distribution of electrical charge. This gives the molecule a weak but permanent dipole moment. This might sound technical, but it's the difference between a simple radiator and a super radiator. This permanent dipole allows HD to emit radiation far more efficiently, especially at the very low temperatures, just tens of degrees above absolute zero, that characterized the outer regions of those collapsing primordial clouds. This enhanced cooling capability could have been a game changer. In regions where the abundance of deuterium was just right, the presence of HD would have allowed the gas to cool down much faster and to significantly lower temperatures than molecular hydrogen could achieve alone. This more efficient heat loss would have led to the fragmentation of the massive parent cloud. Instead of a single, enormous clump collapsing into one supermassive star, the cloud could have broken apart into several smaller, denser knots. Each of these knots could then have collapsed on its own to form a star. This theory opens the door to the possibility of a first generation of stars that included not only the legendary giants but also smaller, more sun-like stars. Some models even suggest that a fraction of these low-mass population 3 stars might still be shining today, hidden in the halos of galaxies, waiting to be discovered as living fossils from the cosmic dawn. The search for evidence to support this nuanced view is a major driving force in modern cosmology. Astronomers use incredibly sophisticated computer simulations to model the conditions of the early universe, carefully adding the physics of HD cooling to their calculations. The results often show a more complex and varied stellar nursery than models that only include H2. The next step is observational. While we cannot yet directly image an individual population 3 star, the next generation of telescopes, like the James Webb Space Telescope, is designed to probe the most distant galaxies, some of which may be illuminated by the light of these first stars. By studying the chemical fingerprints in their light, we might one day detect the signature of HD's influence, confirming that the first chapter of star formation was a story of diversity, not just of unimaginable scale. While the vast, empty stretches between galaxies were the sparse nurseries for the very first molecules, the next great leap in cosmic chemistry required a more concentrated environment. This brings us to the era of the first protogalaxies, the ancestors of the majestic spirals and ellipticals we see today. These weren't the grand structures we know now. They were small, chaotic, and dense clumps of dark matter and gas, each holding perhaps 1,000,000 times the mass of our Sun. It was within these deeper gravitational wells that the story of molecules evolved from a simple tale of survival into a complex drama of creation and destruction. The fundamental shift was one of density and gravity. In the diffuse intergalactic medium, atoms were so spread out that a successful molecular collision was a rare event. But within a protogalaxy, the game changed completely. The stronger gravitational pull of the concentrated dark matter halo drew in vast amounts of primordial gas, compressing it to densities thousands of times greater than the cosmic average. This wasn't just a minor improvement, it was a revolution in chemical opportunity. In this crowded environment, hydrogen atoms were constantly bumping into one another. The inefficient 3-body reactions that struggled to form H2 in the void suddenly became commonplace. These protogalaxies became incredible factories, churning out molecular hydrogen on an industrial scale, creating vast cold reservoirs of the star-making fuel. But with this bounty came a new and powerful actor, feedback from the first stars. The very first population 3 stars to ignite within these protogalaxies were unlike anything that exists today. They were colossal, ferociously bright, and poured out immense amounts of ultraviolet radiation. This radiation was both a creator and a destroyer of molecules. In the dense clouds far from these first stars, the UV light was too weak to penetrate, allowing chemistry to proceed unimpeded. But for any molecule drifting too close to a stellar powerhouse, that same radiation was a death sentence. A single, energetic ultraviolet photon can easily break apart a molecular hydrogen bond, a process known as photodissociation. The first stars, therefore, began to carve out their own environments, creating vast, sterile bubbles of ionized hydrogen around them where molecules could not survive. This created a dynamic and turbulent landscape within the protogalaxy. Imagine a scene of constant upheaval. In the dark, cold cores of giant gas clouds, molecules formed in incredible abundance, cooling the gas and triggering the collapse of new stars. Meanwhile, the brilliant light from those newborn stars simultaneously worked to tear apart the very molecular clouds that spawned them and their siblings. It was a cosmic feedback loop of the highest order, a cycle of construction and demolition that regulated the pace of star formation and ultimately shaped the evolution of the first galaxies themselves. The chemistry was no longer a simple process. It was a delicate dance dictated by the balance between gravity's pull and radiation's push. This complex environment also set the stage for the next great chemical revolution, the formation of the first heavy elements and dust. Those first massive stars lived short, violent lives and ended their days in titanic supernova explosions. These explosions did more than just light up the cosmos. They forged entirely new elements: carbon, oxygen, silicon, iron, and blasted them out into the surrounding gas. Suddenly, the pristine hydrogen-helium environment of the protogalaxy was polluted with the raw ingredients for an entirely new kind of chemistry. The most crucial innovation was the formation of the first microscopic dust grains. These tiny particles, likely made of carbon and silicon compounds, provided a far more efficient surface for the formation of molecular hydrogen than the rare three-body collisions or hypothetical dark matter particles. A hydrogen atom could stick to a dust grain, slide along its surface, and meet another atom, forming a molecule and then releasing it back into the gas. This process, called catalytic formation on dust grains, is orders of magnitude more efficient than any gas phase reaction. With the introduction of even a minuscule amount of dust, the protogalaxy could suddenly produce molecular hydrogen at a staggering rate, filling its interstellar clouds with the coolant needed to form not just massive stars, but entire generations of smaller, longer-lived stars like our Sun. The age of simple chemistry was over. The universe within the confines of these first small galaxies had finally grown rich and complex. For the first few 100,000 years after the Big Bang, the universe was a dark place, its story written in the silent, patient collisions of atoms. But with the dawn of the first light, that story gained a new, explosive chapter, one of creation and destruction happening in the same instant. This light didn't just illuminate the cosmos, it fundamentally reshaped the chemical landscape, turning molecule formation into a delicate, high-stakes balancing act. The very first light to fill the universe wasn't from a star. It was the afterglow of creation itself, the cosmic microwave background radiation. As the hot plasma of the Big Bang cooled and cleared, this faint radiation was unleashed, bathing everything in a warm, uniform glow. For the first fragile molecules, this gentle light was not a threat. Its photons were relatively low energy, having been stretched and cooled by the universe's expansion. In fact, this ambient warmth might have even provided just enough energy to help facilitate some of those early, tentative bonding reactions without being so violent as to tear them immediately apart. It was a soft, universal backdrop against which the first chemical bonds could tentatively form. But this peaceful era was short-lived. The true game-changer arrived with the ignition of the first stars. These weren't just sources of light, they were maelstroms of raw energy pouring out immense amounts of ultraviolet radiation. A single ultraviolet photon from one of these stellar behemoths carries far more energy than a photon from the cosmic microwave background. For a molecule like molecular hydrogen drifting peacefully in the depths of space, this new starlight was a lethal threat. When an energetic UV photon strikes H2, it doesn't just bounce off. It is absorbed, transferring its energy into the bond that holds the two atoms together. That bond vibrates violently, like a guitar string stretched too tight until it simply snaps. This process is called photodissociation, and it effectively reversed the hard-won progress of chemistry, blasting molecules back into their constituent atoms. This created a stark new reality, a universe divided. Imagine a massive, brilliant population 3-star at the heart of a nascent protogalaxy. Around it, its intense UV radiation carved out a vast, sterile bubble of ionized gas, a region known as an H2 region. Within this bubble, the formation of any new molecules was impossible, and any existing molecules that wandered in were quickly obliterated. The size of this destructive sphere was immense, potentially stretching for hundreds of light years. Yet, just beyond the edge of this bubble, in the deep, cold shadows of giant molecular clouds where the star's fierce light could not penetrate, chemistry could proceed unimpeded. Here, in the dark, hydrogen atoms continued to find each other and bond, building up vast reservoirs of molecular fuel. This constant tug of war between formation and destruction became one of the most critical regulatory forces in the early universe. It dictated where and when stars could form. A new star could only be born in a dense, cold cloud of molecular hydrogen. But once that star ignited, its own light began to destroy the very cloud that created it, shutting down star formation in its immediate vicinity and potentially limiting its own growth. This self-regulating feedback loop prevented all the available gas in a protogalaxy from collapsing into stars at once. It ensured that star formation was a gradual process, spread out over time and space, which ultimately allowed galaxies to evolve into the stable structures we see today rather than burning out in a single, brilliant flash. The influence of this first starlight extended beyond mere destruction. It also paved the way for a more complex chemistry. While UV radiation was busy breaking apart simple molecules like H2, it was also providing the energy needed to forge new, more complex bonds. For instance, the same UV photons that dissociate molecular hydrogen can also ionize atoms, knocking electrons free and creating a zoo of reactive ions. These charged particles are far more likely to engage in chemical reactions than their neutral counterparts. In the irradiated outskirts of those destructive bubbles, where the UV light was strong but not overwhelming, a rich and complex photochemistry could occur, potentially leading to the formation of more advanced molecular species than would ever be possible in the total dark. The first light was both a destroyer of worlds and a creator of new chemical possibilities, setting the stage for the universe's eventual journey toward complexity and life. So far, we've seen how the first molecules formed in the quiet, cold darkness or in the violent hearts of exotic objects. But there is another, more pervasive force that could have jump-started chemistry across the entire cosmos: cosmic rays. These are not rays of light, but rather atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light by some of the universe's most powerful engines. In the modern era, we know they come from supernova explosions, active galactic nuclei, and other high-energy events. But in the very early universe, before the first stars even died, where did they come from? Theorists propose that even the infant cosmos had its own sources, perhaps from the explosive evaporation of primordial black holes or from the violent shocks created during the collapse of the first protogalaxies. Wherever they came from, these first cosmic rays may have been the universal match that lit the chemical fire. The challenge for early chemistry was the incredible shyness of neutral atoms. Two hydrogen atoms drifting through the void are electrically neutral. They have no strong inclination to interact. For them to form a bond, they need a very specific, rare three-body collision to shed their excess energy. It's a bit like trying to get two perfectly smooth, magnetically neutral ball bearings to stick together. They just bounce apart. Cosmic rays offer a brilliant solution to this problem through the power of ionization. Imagine one of these high-speed protons, a cosmic ray, screaming through a cloud of pristine hydrogen. It doesn't gently interact. It smashes into a neutral hydrogen atom like a cannonball, with enough energy to knock its electron clear off. In an instant, that neutral atom is transformed into a positively charged ion, a lone proton now buzzing with electrical charge. This act of ionization changes the entire chemical game. A charged particle is incredibly reactive. It desperately wants to regain its balance by finding another electron. This creates a cascading effect. That lonely proton, now a reactive hydrogen ion, will aggressively attract a nearby neutral hydrogen atom. When they meet, they can form a molecular hydrogen ion, H2+. This ion is itself unstable, but it's a crucial stepping stone. It can then readily collide with another neutral hydrogen atom, and in a final act of chemical teamwork, transfer its charge to form a stable, neutral molecule of H2, releasing the original proton back into the wild to ionize another atom and begin the process all over again. This catalytic cycle is far more efficient than waiting for a rare three-body collision. A single cosmic ray particle, with its immense energy, can initiate a chain reaction that produces thousands of molecular hydrogen molecules as it travels through a cloud of gas. It acts as a roving chemical catalyst, tirelessly forging bonds in its wake. This means that regions of the early universe that were constantly peppered by these first cosmic rays could have become incredibly fertile grounds for molecule production, building up the molecular fuel needed for star formation much faster than quieter, more isolated regions. The influence of cosmic rays might extend even beyond simple hydrogen. As the first supernova began to explode, they would have seeded the environment with trace amounts of heavier elements and, crucially, generated an even more intense background of cosmic radiation. This could have accelerated the formation of more complex molecules. For instance, a cosmic ray could ionize a helium atom or a trace carbon nucleus, creating a highly reactive ion that could then attract and bond with other atoms, potentially leading to the first tentative steps toward the molecular diversity that would later fill interstellar clouds. In this way, cosmic rays may not have just helped build the universe's first fuel. They could have also been the midwives for its first steps toward genuine chemical complexity, turning the vast emptiness of space into a subtle but prolific chemical factory. But to truly understand the molecular dawn, we must move beyond these individual theories and examine the comprehensive picture painted by some of the most sophisticated digital reconstructions of the early cosmos. This brings us to the intricate world of dark age chemistry models. The period between the release of the cosmic microwave background and the ignition of the first stars, often called the cosmic dark ages, was anything but chemically inert. It was a dynamic, if subtle, era where the fate of the first molecules was being decided. Modern astrophysicists use immense computer simulations to rewind the clock and recreate this elusive chapter, building virtual universes governed by the precise laws of physics and chemistry. These simulations are staggering in their complexity. They don't just track the gravitational collapse of gas. They incorporate vast networks of chemical reactions, sometimes hundreds of different interactions between atoms, ions, electrons, and photons. The simulation code must account for the rate of every possible process. Two hydrogen atoms colliding with an electron to form H2, a helium hydride ion meeting a hydrogen atom and exchanging partners, the photodissociation of a fragile lithium hydride molecule by a stray photon from the fading cosmic microwave background. Each reaction has a probability that depends on the local temperature, density, and radiation field. The computer's task is to calculate the outcomes of these countless interactions across millions of years and light years, slowly building a timeline of chemical evolution from a simple soup of atoms to a richer molecular mixture. The primary goal of these digital laboratories is to generate a prediction, a precise map of the abundances of key species like molecular hydrogen, hydrogen deuteride, helium hydride, and lithium hydride at various points in time and in different cosmic environments. Would H2 be uniformly spread or clustered in specific density enhancements? Would the rare He H+ ions survive long enough to be significant, or would they be rapidly destroyed? The models answer these questions by letting the virtual chemistry play out, providing a detailed forecast of what our telescopes should be looking for. These predictions, however, are not the end of the story. They are the beginning of a crucial dialogue with observation. The real power of these models is that they create testable hypotheses. Astronomers then take these predictions and compare them to the few observational constraints we have from the real universe. For instance, we can study extremely distant, ancient clouds of gas by analyzing the light from even more distant quasars as it passes through them. These clouds act as cosmic fossils, preserving a record of their chemical composition from a time very close to the Dark Ages. By measuring the absorption lines in the quasar's spectrum, scientists can determine the actual abundance of molecules like H2 and HD in these primordial pockets. This is where the models are put to the test. Do the simulated abundances match the observed ones? Often, the first run of a simulation does not. An initial model might predict far more molecular hydrogen than we actually detect. This discrepancy is not a failure, it is a discovery. It tells the modelers that they are missing a piece of the puzzle. Perhaps they have underestimated the destructive power of a subtle background radiation field. Or maybe there is a destructive chemical pathway, a reaction that destroys H2 that they haven't yet included in their network. They then refine the model, adding new physics or chemistry, and run it again. This iterative process of prediction, observation, and refinement is how we slowly close in on the truth. These ongoing comparisons have already led to significant insights. The observed abundances of H2 and HD in the early universe are lower than the simplest models predicted, suggesting that some universal process was actively inhibiting their formation or enhancing their destruction. This has fueled investigations into the roles of things like a pervasive cosmic ultraviolet background from the earliest stars or the catalytic destruction of molecules on the surface of the first dust grains. Each mismatch between model and observation forces us to think more creatively, to consider actors and processes we might have previously overlooked. In this way, the Dark Ages are being illuminated not by light, but by the relentless logic of computation, guiding us toward an ever sharper understanding of our molecular origins. While the chaotic dance of particles and radiation set the stage for early chemistry, another, more subtle force may have been directing the movement from the shadows: magnetism. We often think of the early universe as a formless, expanding fireball, but it might have been subtly structured by nascent magnetic fields, threads of invisible influence that could have guided the very first chemical handshakes. The question of where these primordial fields came from is a mystery in itself. Some theories suggest they were born from the violent turbulence of the phase transitions in the super-hot early cosmos, while others propose they were generated by the dynamics of the plasma itself, tiny magnetic seeds stretched to cosmological scales by the inflationary expansion of the universe. However they originated, even a faint, large-scale magnetic field could have had a profound effect on the formation of the first molecules. To understand their potential influence, we need to consider the environment. Before atoms formed, the universe was a seething plasma of charged particles, free protons, electrons, and helium nuclei. Charged particles behave very differently in the presence of a magnetic field than they do in empty space. Instead of moving in straight lines, they are forced to spiral along the magnetic field lines, corralled by this invisible force. This changes everything about how they interact. In a universe without magnetic fields, these particles would zip around in all directions, and a collision would be a matter of random chance. But with even a weak magnetic field present, their motion becomes more organized, more focused. Ions and electrons are effectively funneled, their paths aligned by the field's architecture. This isn't just a minor adjustment. It dramatically increases the likelihood that two particles will meet. This organized motion could have been a powerful catalyst for chemistry, particularly for the formation of molecular ions, which are believed to be crucial stepping stones to stable neutral molecules. Take, for example, the formation of the helium hydride ion, He+. A positively charged helium ion and a proton would both be compelled to spiral along the same magnetic field lines. Their guided paths would make a collision far more probable than in a purely random, unmagnetized plasma. Once formed, this molecular ion itself would be charged and thus also under the influence of the magnetic field, potentially guiding it toward its next reaction, such as meeting a free electron to form neutral helium hydride or encountering a hydrogen atom. The magnetic field, in this scenario, acts as a universal matchmaker, efficiently bringing reactive partners together and dramatically speeding up the rate of chemical evolution in the infant cosmos. The influence wouldn't stop with ions. Even after recombination, when neutral atoms formed, magnetism could have continued to play a role through a process known as ambipolar diffusion. In a partially ionized gas where some particles are neutral but others, like free electrons, are still charged, the magnetic field only directly affects the charged components. These charged particles, as they spiral along the field lines, can drag the neutral atoms along with them through collisions. This process can help to concentrate matter along magnetic field lines, increasing the local density in specific regions. For molecule formation, density is everything. By gathering atoms and ions into denser filaments and sheets, these primordial magnetic fields could have created the perfect high-density environments where the inefficient three-body reactions needed to form molecular hydrogen suddenly became efficient and commonplace. This theory suggests that the first molecules may not have formed uniformly throughout space, but rather in specific, magnetically focused ribbons and structures. The cosmic web of galaxies we see today, with its vast filaments and voids, might have its origins not just in gravitational density fluctuations, but also in the pattern of these primordial magnetic fields. They could have provided the initial blueprint that guided the flow of matter, making some regions incredibly fertile for chemistry and star formation while leaving others barren. The legacy of these fields might even persist today, woven into the fabric of galaxies, their original imprint stretched and amplified over billions of years. While the direct detection of such ancient, weak magnetic fields remains an immense challenge for astronomers, their potential role presents a compelling vision of an early universe that was not a formless chaos, but a realm subtly ordered by invisible forces, gently shepherding atoms together to write the first chemical words of the cosmic story. Now consider for a moment the environment of that primordial universe. It was not only vast and empty, but it was also profoundly cold, cooling rapidly from its initial unimaginable heat to temperatures just a few tens of degrees above absolute zero. In such a deep chill, atoms and particles move incredibly slowly, their thermal energy dropping to a mere whisper. This presents a monumental problem for chemistry as we classically understand it. For two hydrogen atoms to form a bond, they must overcome a natural repulsion between their positively charged nuclei. To do this, they need a certain minimum amount of energy, a kinetic kick, to smash through this repulsive barrier and get close enough for their electron clouds to merge and create a stable bond. In the frigid early cosmos, most atoms simply did not have this energy. By all classical accounts, the formation of that first molecular hydrogen should have been an impossibly slow, almost negligible process. Yet we know it happened. The universe found a way, and it did so by bending the very rules of reality through a phenomenon known as quantum tunneling. This is where our understanding of physics must shift from the large-scale, predictable world we experience to the bizarre and counterintuitive realm of quantum mechanics. In the quantum world, particles are not just discrete balls, they are also waves with a certain probability of existing in different places. This wave-like nature allows for a truly astonishing possibility. A particle can, in a sense, appear on the other side of an energy barrier without ever having to go over the top of it. Imagine a ball rolling up a hill. Classically, if it doesn't have enough energy to reach the summit, it will roll back down. But if that ball behaved like a quantum particle, there's a finite, calculable chance that it could simply vanish from one side of the hill and reappear on the other, as if it had dug a tunnel straight through. It doesn't break the laws of physics. It operates on a deeper, more fundamental set of rules. Apply this to our two lonely hydrogen atoms drifting together in the cold dark. Classically, they approach each other, but their combined kinetic energy is too low to overcome the electric repulsion pushing their nuclei apart. They should just bounce off each other and drift away, their chance for union lost. But quantum mechanics offers a second chance. There is a probability, however small, that the wave function of one nucleus will overlap with the wave function of the other on the far side of that energy barrier. In that fleeting quantum moment, the two atoms disregard the classical wall separating them and simply tunnel through it, instantly finding themselves in the bonded state of a hydrogen molecule. They achieved reaction without ever possessing the classical energy required to do so. This process wasn't just a minor contributor. Theorists suggest it may have been the dominant mechanism for forming molecular hydrogen in the coldest, quietest regions of the early universe, where thermal energy was virtually non-existent. It helps explain how enough of this crucial molecule accumulated to begin the process of cooling and collapse, even in environments that were seemingly too cold for any chemistry to occur. Quantum tunneling provided a universal backdoor, a loophole in the laws of energy that allowed the first bonds to form against all classical odds. It underscores a profound truth about our cosmos. The universe is not merely a classical machine. It is a quantum entity at its very heart, and its first chemical steps were guided by the strange and wonderful principles of the subatomic world. But to push the boundaries of what we consider a molecule, we must venture back to a time when the very concepts of atom and nucleus had no meaning whatsoever. This takes us to the first microseconds after the Big Bang, to a state of matter so extreme it defies ordinary comprehension, the quark-gluon plasma. In this seething, primordial soup, the universe was too hot and dense for protons and neutrons to exist. Instead, their constituent particles, quarks and gluons, roamed freely, unbound by the powerful nuclear force that would later lock them away inside atomic nuclei for eternity. It was a state of pure, deconfined energy, a chaotic ocean where the very building blocks of matter were liberated. The notion of a molecule here seems not just unlikely, but utterly impossible. Yet, some theorists dare to ask, could there have been precursors, fleeting echoes of structure, even in this inferno? The idea isn't that familiar molecules like water or carbon dioxide could exist in this plasma. That would be akin to expecting a snowflake to form in the heart of the sun. Instead, the question shifts to whether any form of transient, bound structure could arise between the fundamental particles themselves. Quarks carry something called color charge, which is the source of the strong nuclear force, and they are constantly exchanging gluons which mediate that force. In the incredible density of the early universe, this constant interaction could have led to brief, localized correlations, dense clusters or waves within the plasma that behaved in a loosely coordinated way. These wouldn't be molecules as defined by shared electrons, but perhaps they were a more primitive kind of association, a whisper of order in the chaos, a hint of connection before true chemistry was even possible. We can actually recreate minute versions of this primordial state today in powerful particle colliders like the Large Hadron Collider. By smashing heavy ions together at nearly the speed of light, physicists can, for a fleeting instant, generate a tiny fireball of quark-gluon plasma and study its properties. And what they observe is fascinating. This plasma doesn't behave like a simple gas. It flows with incredibly low viscosity, like a perfect, frictionless liquid. This suggests a very high degree of interaction and coordination among the quarks and gluons, a collective behavior that is far more structured than random chaos. While we don't see discrete molecular bonds, we see a system that is exquisitely organized on a fundamental level, capable of acting as a unified whole. This hints that the infant universe in its hottest moment may have possessed a latent capacity for complexity that would only express itself fully once it cooled. Another speculative idea involves the potential for exotic, short-lived particles that don't exist in our current, colder universe. In those first moments, energies were so high that the laws of physics might have allowed for temporary formations that were something more than a quark and something less than a proton. Some theories even suggest the possibility of 4 quark or 5 quark particles, known as tetraquarks and pentaquarks, which have been observed briefly in colliders. Could these bizarre composite states have acted as the universe's very first supraatomic structures? They would have been utterly unstable, forming and vanishing in fractions of a nanosecond, but for that instant, they would have represented a new level of architectural complexity in the cosmos. They were not molecules, but they were a step beyond a lone quark, a tentative experiment in building something more. Ultimately, the quark-gluon plasma era represents the absolute ground floor of material existence. It is the baseline from which all complexity emerged. While it is almost certain that no true molecules could survive there, its properties were the direct cause of everything that followed. The way it cooled, the way it transitioned into the first protons and neutrons, set the precise stage for the nuclear fusion that would occur minutes later during Big Bang nucleosynthesis, forging the hydrogen, helium, and deuterium that would become the raw ingredients for the first real molecules. So even if no bonds formed in that initial fire, the plasma was the crucible that cast the pieces. It was the anarchic workshop where the universe forged the very tools it would later use to build itself, a chaotic beginning that held within it the perfect potential for all the order to come. This brings us to a theory that steps beyond the mechanics of physics and into the realm of profound philosophical inquiry, the anthropic-principle and its startling connection to the universe's first chemical handshake. The principle itself, in its simplest form, observes that the universe we are capable of observing must, by necessity, be compatible with our existence as observers. We see the laws of physics and the fundamental constants of nature as being finely tuned, not because they were designed that way, but because if they were even slightly different, we wouldn't be here to wonder about them. Apply this logic to the story we've been unraveling, and a captivating possibility emerges. The specific, seemingly precarious pathway to forming molecular hydrogen wasn't just one option among many. It may have been the only option that could ever lead to us. Think about the delicate chain of events we've explored. The universe had to cool at just the right rate to allow atoms to form during recombination. The quantum mechanical properties of the hydrogen atom had to be precisely what they are to permit the tunneling effect that allowed bonds to form in the cold. The strength of the electromagnetic force had to be set to an exact value to make the hydrogen bond stable, yet not so strong that atoms could never break apart and reform later. The initial density fluctuations from inflation had to be of a specific magnitude large enough to create dense regions where chemistry could thrive, but not so large that the universe immediately collapsed back on itself. At every single step, the conditions had to be exquisitely perfect for molecular hydrogen to accumulate in sufficient quantities to cool the first gas clouds and ignite the first stars. Now consider the alternative. Imagine a universe where the electromagnetic force was slightly stronger. Molecular hydrogen might form more easily, but it might also become so stable that it could never be broken apart by starlight, locking away the universe's primary fuel and preventing the cycle of star birth and death that spreads heavy elements. Or picture a cosmos where the force was slightly weaker. Hydrogen atoms might never overcome their mutual repulsion to bond at all. In that sterile, atomized universe, gas clouds could never cool. Gravity would be forever held at bay by thermal pressure, and the cosmos would remain a perpetual, dark haze of isolated atoms, a diffuse and silent void where no star ever glowed, no planet ever formed, and no life ever arose to give it meaning. The profound implication is that the specific chemistry that allowed for H2 formation might be a non-negotiable prerequisite for a living, breathing, conscious universe. We are not merely passive observers of a process that could have gone any number of ways. We are the direct products of a sequence so precise that its success seems almost miraculous. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of it was forged in stars that could only exist because of the cooling power of those first simple molecules. The anthropic-principle suggests that in a vast multiverse of possibilities, where perhaps an infinite number of universes bloom into existence with different physical laws, we inevitably find ourselves in one of the very few where the chemistry worked out just right. Our existence is the ultimate evidence that the recipe for the first molecules was a success. It is a humbling and awe-inspiring thought. The molecular bonds that formed in the darkness 14 billion years ago were the first necessary words in a story that would eventually include you, me, and everything we have ever known. But what if we've been picturing this cosmic dawn all wrong? Our story so far has often assumed a certain uniformity, a universe where the first molecules formed in a relatively even, if slow, process across the vast expanses of space. Yet, a compelling idea challenges this view, suggesting that the infant cosmos was not a bland, homogeneous soup, but rather a patchwork of distinct chemical environments from the very beginning. This is the heterogeneous universe theory, and it proposes that the first chemical bonds didn't form everywhere in the same way. Instead, the primordial cosmos was a mosaic of different molecular landscapes, each with its own unique story to tell. This chemical diversity didn't arise by chance. It was a direct consequence of the universe's birth pangs. Remember those quantum fluctuations from inflation, the tiny ripples that were stretched into the hills and valleys of density that seeded all future structure. This theory takes that idea a critical step further. It argues that these primordial variations weren't just differences in how much stuff was in a region, but also potentially in what kind of stuff was there and under what conditions. While the overall mixture of hydrogen and helium was remarkably uniform, the local environment, the precise temperature, density, and radiation field in a given patch could have varied significantly from one place to another. And in the delicate dance of early chemistry, where the formation of a single molecule depended on a precise alignment of conditions, even a small local difference could have had a massive cascading effect. Imagine traveling across this newborn universe, in one over-dense region where particles were packed relatively close together. The efficient formation of molecular hydrogen might have taken hold early. This patch would have become a powerhouse for H2 production, quickly building up a rich reservoir of coolant that was poised to be the first to collapse into massive population 3 stars. Just a few hundred light-years away, however, the story could have been completely different. An under-dense region, a valley in the cosmic landscape, would have been far colder and more diffused. Here, the slow quantum tunneling process might have been the only game in town, causing molecular hydrogen to form at a much more lethargic pace and potentially delaying star formation for millions of years. Now, journey to another region, one that was perhaps bathing in a slightly stronger remnant glow from the Big Bang, or had a unique concentration of free electrons. This might have been the perfect nursery for the helium hydride ion, He+. In this pocket of the cosmos, this exotic molecular ion wouldn't have been a fleeting curiosity. It could have been the dominant chemical species, a cornerstone of the local environment. Another area, blessed with a tiny statistical overabundance of the lithium forged in the Big Bang, might have seen the rare and fragile lithium hydride molecule form in detectable quantities, creating a pocket of super-efficient cooling that acted as a stellar ignition switch far faster than its neighbors. This paints a far richer and more dynamic picture of the cosmic dark ages. It wasn't a monotonous, universal waiting period. It was an era of incredible chemical geography, with entire regions specializing in different molecular processes. Some areas were bustling H2 metropolises on the fast track to lighting up the cosmos. Others were quiet, slow-moving backwaters of atomic gas. Some were exotic ports dealing in rare ions like He+, while a few privileged zones might have been lithium hydride hubs, tiny but incredibly efficient engines of collapse. This initial patchwork could have dictated the tempo and mode of the subsequent cosmic dawn. The first stars may not have ignited in a single, synchronized flash across the universe, but rather in a staggered fashion, flickering on first in the most chemically advanced regions, with other areas following suit only as their own local molecular factories finally caught up. The legacy of this primordial heterogeneity might even be written in the stars we see today. The characteristics of the very first stars, their size, their brightness, how quickly they lived and died, were determined by the properties of the gas clouds that formed them. A cloud rich in Hd due to a local overabundance of deuterium would have cooled more efficiently and perhaps fragmented to form smaller stars. A cloud that formed in a region dominated by standard H2 might have only been able to collapse into a single monstrous star. The initial chemical diversity of the universe could have directly seeded a diversity in its first stellar population, a complexity that our models are only beginning to appreciate. We are only now developing the tools to search for these subtle chemical fingerprints across the vastness of space, seeking the echoes of a cosmos that was never simple, but was complex and varied from its very first moments. This leads us to a perspective that reframes the very act of bonding, viewing it not just as a physical process but as a cosmic act of recording. Imagine the universe in its first moments, a seething, probabilistic cloud of quantum potential. Every particle exists in a haze of possibilities, its position, momentum, and energy not yet fixed. This is the universe in a state of pure, unprocessed information. The formation of the first molecules, according to this theory, was the moment this potential began to crystallize into a stable, lasting record. It was the universe's first act of writing its own history, encoding the conditions of its infancy into the very bonds that would build its future. Consider the precise moment two hydrogen atoms decide to form a molecule. For this to happen, a specific and incredibly delicate set of quantum conditions must be met. The wave functions of the two atoms must align, their spins must be compatible, and their kinetic energies must fall within an exact range that allows for either a classical collision or a successful quantum tunnel through the repulsive barrier. The outcome of this event, whether a bond forms or the atoms drift apart, isn't random. It is a direct and sensitive reading of the local environment. The temperature of the surrounding gas, the density of particles, the faint echo of background radiation, even the subtle influence of distant gravitational fields, all of these factors are inputs that determine the probability of that bond being forged. When the bond successfully forms, the resulting molecule isn't just a new chemical entity. It is a stable, physical bit of data. It is a monument to that exact combination of temperature, density, and energy that existed at that precise point in spacetime. It has, in effect, measured its environment and frozen that measurement into its very existence. This transforms our view of the primordial molecular clouds from simple collections of fuel into the universe's first hard drives. A vast cloud of molecular hydrogen isn't just a cold, dark mass waiting to collapse. It is a dense archive, a three-dimensional snapshot of the density fluctuations, temperature variations, and energy distributions of the early cosmos. Each molecule is a pixel in that image, its presence a testament to a specific set of conditions that allowed it to form where others could not. The pattern of where molecules clustered and where they were absent becomes a direct map of the quantum seeds planted by inflation. By studying the distribution and abundance of these ancient molecules, we are not just doing chemistry, we are performing archaeology on the universe's earliest recorded data. The implications of this idea stretch all the way to the nature of life itself. the information processing did not stop with simple hydrogen. As the universe grew more complex, so did its molecular language. The formation of more complex molecules involved ever more intricate quantum calculations, each new bond adding another layer of information to the cosmic record. This process of encoding environmental data into molecular structures arguably reached its apex with the arrival of DNA, a molecule that is quite literally a code. The progression from the first hydrogen bond to the double helix can be seen as a continuous thread of the universe learning to process and store information in increasingly sophisticated ways. The first molecules were the primordial precursors to the genetic code, the initial hesitant steps in a billions of years-long journey toward a universe that could not only record its conditions but eventually come to understand them. Now, let's venture into one of the most fascinating and speculative ideas on our list, a theory that connects the largest-scale phenomena in the universe to the smallest of chemical beginnings. We're talking about primordial gravitational waves. These are not the recently detected ripples from colliding black holes, but something far more ancient and profound, echoes from the violent birth of the cosmos itself, stretching and compressing the very fabric of space-time. The fringe theory we explore now proposes that these ripples did more than just warp the cosmos on a grand scale. They may have directly influenced the microscopic dance of atoms, creating the perfect conditions for the very first molecules to form. To grasp this, we need to understand what a gravitational wave truly is. Imagine space-time not as a static stage, but as a flexible, fabric-like surface. A massive cosmic event like the Big Bang doesn't just send out a flash of light. It sends a shudder through this fabric, a wave that literally stretches and squashes space itself as it travels. Now picture the universe in its first moments, still a hot, dense plasma. As these primordial gravitational waves rippled through it, they wouldn't just be a silent tremor. They would have actively compressed and rarefied the matter in their path. Where space was compressed, particles were pushed closer together. Where space was stretched, they were pulled further apart. This created a traveling pattern of microscopic density fluctuations, a subtle, rhythmic choreography imposed upon the chaotic particle soup. This is where the theory makes its leap. For the first molecules to form, density was everything. The chance of two hydrogen atoms meeting and successfully bonding was incredibly sensitive to how closely they were packed. In the vast, average emptiness of the early universe, these chances were slim. But within the microscopic, high-density pockets created by a passing gravitational wave, the rules of the game changed dramatically. For a fleeting moment in that compressed region, the local density of particles could have spiked. Atoms that were light years apart on average were suddenly neighbors, dramatically increasing the collision rate. In these temporary, wave-induced hotspots, the rare three-body reactions needed to form molecular hydrogen could have become not just possible, but highly efficient. It would be like a universal pressure cooker, turning up the heat and pressure in a precise, localized way to catalyze a reaction that was stagnant everywhere else. The implications are staggering. It suggests that the first chemistry in the universe may not have been a slow, steady simmer, but a rhythmic, wave-driven process. The formation of molecules could have occurred in pulses correlated with the passage of these space-time ripples. Dense filaments of gas, shaped by the gravitational wave background, might have become the preferred sites for this early chemistry, creating a lace-like pattern of molecular richness woven into the cosmos. This theory provides a potential physical mechanism for why some regions of the early universe became chemically active faster than others. They were simply in the right place at the right time to be squeezed by a gravitational wave, giving them a head start on building the molecular fuel for the first stars. Of course, this remains a highly speculative and difficult-to-prove idea. Detecting the primordial gravitational wave background itself is one of the holy grails of cosmology, with experiments like space-based interferometers searching for its faint imprint on the cosmic microwave background. Proving a direct causal link between those waves and specific molecular abundances feels like a distant dream. Yet, it's a powerful concept because it unifies the physics of the unimaginably large with the impossibly small. It proposes that the same tremor that shaped galaxies also guided the first handshake between two atoms, linking the grand architecture of the cosmos to the humble beginnings of chemistry in a single, elegant, and rhythmic dance. But the quest to understand our molecular origins doesn't stop with the known particles of the Standard Model. To push deeper, we must venture into the realm of the hypothetical, to a grand theoretical framework that promises to unite the fundamental forces of nature, supersymmetry. This elegant concept, often nicknamed SUSY, proposes that every known particle has a hidden superpartner, a heavier, more exotic twin. While we have yet to directly detect these superparticles, their potential influence on the cosmic story is profound. One compelling theory suggests that in the unimaginable energy of the first instance after the Big Bang, the decay of these supersymmetric particles didn't just create the matter we know. It may have actively seeded the cosmos with the very first molecular building blocks. To appreciate this idea, we need to step into the bizarre world of the early universe, a place where energy was so concentrated that the distinctions between particles we consider separate today were blurred. In this seething cauldron, supersymmetric particles would have been abundant, constantly popping in and out of existence. As the cosmos expanded and cooled, these heavy, unstable superpartners would have begun to decay, transforming into the lighter, more familiar particles of our current universe. This process is thought to be a key candidate for explaining the mysterious imbalance between matter and antimatter that allowed our universe to survive. But the theory goes a step further, proposing that these decays were not perfectly clean. Instead of just producing lone quarks or electrons, certain decay pathways could have yielded clusters of particles that were already loosely bound together. Not full atoms, but the next best thing, molecular ions or highly excited, unstable compounds that were the direct precursors to stable molecules. Imagine the decay of a specific superparticle, a theoretical object like a neutralino. As it breaks down, it doesn't just release a random spray of energy and fundamental particles. The intricate rules of supersymmetry could have dictated that its decay products include complex, short-lived states like protonium, a bound state of a proton and an antiproton, or other exotic hadronic molecules. While these entities would have been incredibly unstable, vanishing in fractions of a nanosecond, their brief existence could have had a cascading effect. Their decay would have released a shower of energy and secondary particles into the surrounding plasma in a very specific, localized way. This could have created microscopic hotspots of high density and unusual chemistry, tiny environments where the formation of more stable molecules like molecular hydrogen ions became not just possible but probable. In this view, the first seeds of chemistry weren't sown slowly and uniformly, but were broadcast across the cosmos in a brilliant flash of decaying superparticles, each decay acting as a tiny chemical catalyst. The beauty of this theory is that it provides a potential physical mechanism for a problem we've encountered before. How did molecular formation happen so efficiently in a universe that was, on average, so incredibly sparse? The decays of supersymmetric particles would have been like countless microscopic fireworks going off, each one creating a temporary, high-density environment perfect for jump-starting chemical bonds. This process would have been especially crucial in the very earliest moments, before the universe had cooled enough for traditional routes to molecule formation to become effective. It suggests that the infrastructure for chemistry was laid down astonishingly early, woven into the fabric of the universe by the same physics that determined the fate of matter itself. The search for evidence, while immensely challenging, is not entirely out of reach. Precision studies of the cosmic microwave background and the primordial abundances of light elements could one day reveal subtle anomalies that point towards these exotic early processes, offering a glimpse into a cosmic dawn illuminated not just by the first light, but by the last breaths of the universe's most mysterious particles. Yet another possibility pushes our understanding of a molecule to its absolute limit, venturing from the realm of chemistry into the strange world of quantum collective behavior. This is the theory that the first coherent molecular structures might not have been formed through bonds in the traditional sense at all, but through an exotic state of matter known as a Bose-Einstein condensate. To grasp this, we need to shift our perspective entirely. We typically imagine atoms as discrete, individual particles bouncing around independently, only linking up when they physically collide and share electrons. But quantum mechanics reveals a different potential, one where identity itself becomes blurred and a vast collection of particles can begin to behave as one single, unified quantum object. The conditions for such a phenomenon are incredibly specific and require temperatures achingly close to absolute zero. In the modern lab, creating a Bose-Einstein condensate is a monumental achievement involving sophisticated lasers and magnetic traps to cool a small cloud of atoms to within a billionth of a degree above absolute zero. At these profound depths of cold, the atoms lose their individual identities. Their quantum wave functions, which usually define the probability of where each atom is, begin to overlap and merge. They cease to behave like a gas of separate particles and instead start to act in perfect lockstep like a single superatom. This entity is governed by one unified wave function, a macroscopic demonstration of quantum weirdness. Now apply this concept to the early universe. While we often picture it as intensely hot, it was also expanding and cooling at a staggering rate. There would have been a very brief but critical window of time when certain regions, particularly the deepest, darkest voids far from any nascent energy sources, could have plunged to temperatures low enough to facilitate this bizarre quantum transition. And the most abundant element, hydrogen, has an isotope whose properties make it a prime candidate for this behavior. When a hydrogen atom's proton and electron have aligned spins, it's called orthohydrogen, which behaves as a fermion and resists this kind of collective behavior. But when the spins are opposite, it's known as parahydrogen, and it is a boson. Bosons are the class of particles that are allowed to occupy the same quantum state, which is the fundamental requirement for forming a Bose-Einstein condensate. The theory suggests that in these ultra-cold, ultra-quiet pockets of the primordial cosmos, a vast cloud of parahydrogen could have undergone this quantum phase transition. Trillions upon trillions of atoms would have shed their individuality to coalesce into a single, giant quantum entity. This wouldn't be a molecule held together by electromagnetic forces between electrons and nuclei. There would be no chemical bond as we define it. Instead, it would be a molecule in a much broader, more profound sense, a single, coherent structure of matter defined by a shared quantum state. It would be less like a handshake between two atoms and more like an entire crowd of people suddenly moving and breathing in perfect, silent unison. The implications of such an entity existing in the infant universe are fascinating. A Bose-Einstein condensate has very unique properties, including something known as frictionless flow or superconductivity. If such a vast quantum cloud existed, how would it interact with the gravitational tides of the first density fluctuations? Could its coherent, frictionless nature have allowed it to flow and collapse in ways that normal gas simply could not, perhaps seeding the first structures through quantum effects on a macroscopic scale? Its presence would represent a third path to complexity, separate from the slow accumulation of chemical bonds or the violent catalysis of exotic particles. It would mean that the universe was not just building itself through chemistry and gravity, but was also capable of harnessing the most counterintuitive aspects of quantum physics to create order on a grand scale. While this remains one of the more speculative ideas, it challenges our very definitions and reminds us that the early cosmos was a laboratory for physics far beyond our everyday experience. Yet, even with catalysts and quantum tricks, the sparse early universe presented a colossal challenge: how to gather atoms together frequently enough for chemistry to truly take off. This puzzle leads us to a powerful and pervasive physical force that may have churned the primordial gas into a fertile ground for molecules turbulence. We often picture the cosmos after the Big Bang as a serene, expanding void, a placid sea of slowly drifting atoms, but this quiet image is likely an illusion. A growing body of theory suggests the infant universe was a dynamic, chaotic, and intensely violent place, where supersonic turbulence provided the essential pressure and compression needed to forge the first bonds at a scale and speed that gravity alone could not achieve. To understand how, imagine a perfectly still cloud of hydrogen gas. Atoms drift slowly and collisions are rare, peaceful events. Now inject energy into this system. Something stirs it up, creating whirlpools, eddies, and powerful shock waves that race through the gas at speeds far exceeding the speed of sound. This is turbulence, and it completely transforms the environment. Within this chaotic flow, atoms are no longer drifting, they are being slammed together. Vast streams of gas collide, creating microscopic regions of immense pressure and density at the shock fronts where they meet. In these temporary, violent hotspots, the local density can spike by orders of magnitude. It's the difference to trying to start a fire by gently rubbing two sticks together in still air versus holding them in the jet of a hurricane. The turbulence provides the intense, focused energy required to make the reaction not just possible but inevitable. The critical question then becomes, what was the engine for this primordial turbulence? Gravity itself provides one compelling answer. As the first dark matter halos began to condense from the cosmic web, they didn't just gently pull gas in, they did so in a clumpy, chaotic manner. Infalling streams of gas from different directions would have collided, creating a natural and sustained source of supersonic turbulence within the collapsing protogalaxies. This wasn't a smooth process, it was a violent cacophony of colliding flows, a chaotic ballet directed by gravity's invisible hand. Within this maelstrom, the shock waves generated by these collisions would have acted as incredible molecular forges. The momentary but extreme compression in these shocks dramatically increased the collision rate between atoms, making the formation of molecular hydrogen through three-body reactions not just a rare occurrence, but a frequent and efficient event along these vast, rippling wavefronts. But gravity wasn't the only sculptor of this chaotic early environment. A second, and perhaps even more powerful, source of turbulence emerged with the ignition of the very first stars. These stellar behemoths did not live quiet lives. They poured out not only intense ultraviolet radiation but also powerful supersonic winds of charged particles. As these winds slammed into the surrounding pristine gas, they acted like cosmic plows, pushing the material outward and creating enormous, expanding bubbles of shocked and compressed gas at their edges. Furthermore, when these short-lived giants finally died, they did so in spectacular supernova explosions, detonating with unimaginable force. The blast waves from these first supernovae would have raced through the intergalactic medium at thousands of kilometers per second, violently shocking and compressing any gas they encountered. This stellar feedback didn't just destroy molecules, it also created the ideal conditions for a new, more prolific wave of chemistry to begin. This creates a fascinating picture of a regulated cycle. The first stars, born from the gentle, turbulence-aided collapse of gas, then retroactively reshaped their entire environment. Through their winds and explosive deaths, they seeded their surroundings with intense turbulence, which in turn compressed new clouds of gas, catalyzed the rapid formation of fresh molecular hydrogen, and triggered the collapse of the next generation of stars. It was a self-perpetuating cycle of creation and destruction, with turbulence acting as the universal mechanic, both building up and tearing down the structures within these first galaxies. This process ensured that star formation did not consume all available fuel at once, but instead became a sustained process, gradually building up the complex structures we see in galaxies today. The echoes of this primordial chaos, this essential turbulence, are likely still woven into the fabric of star-forming clouds across the cosmos, a lasting testament to the violent and dynamic birth of everything we see. While lithium hydride itself is a fascinating subject, the story of lithium's role in the early universe doesn't end there. It branches off into even more exotic and tenuous possibilities, involving molecular species so rare they push the boundaries of what we can even hope to detect. This brings us to the world of alternative lithium chemistry and two particularly intriguing theoretical players, the lithium hydride ion known as Li-H+, and the dilithium molecule Li2. The lithium hydride ion is exactly what it sounds like, a molecule of lithium hydride that has lost an electron, giving it a positive charge. Its formation would have been a delicate and specific affair. Picture a neutral lithium atom and a hydrogen atom drifting together. If they were bathed in the faint, residual ultraviolet light from the fading afterglow of the Big Bang or the very first stellar objects, that light could have provided just enough energy to ionize a standard lithium hydride molecule immediately after it formed, knocking an electron loose and creating Li-H+. Alternatively, a highly energetic cosmic ray could have smashed into a pre-existing Li-H molecule, stripping an electron away in the collision. This charged molecule would have behaved very differently from its neutral counterpart. Its positive charge would have made it incredibly reactive, eager to interact with any free electrons or other particles it encountered, potentially acting as a catalyst for other, more complex reactions in a way that neutral molecules could not. The existence of even a minuscule amount of Li-H+ could have had a subtle but important impact. As a molecular ion, its spectral signature would be distinct and potentially easier to detect in certain wavelengths than neutral Li-H. More importantly, its presence would be a direct tracer of the radiation environment in the early cosmos. Detecting it would tell us not only about chemistry, but also about the intensity and type of the very first light sources that began to illuminate the darkness, providing a unique window into the conditions that prevailed as the first stars began to wake up. Then there is the dilithium molecule, Li2, a truly speculative and fascinating concept. This would involve two lithium atoms finding each other and bonding in the vast, empty expanse of the primordial universe. The odds of this happening were astronomically low, far worse than for the formation of even lithium hydride. For Li2 to form, two of the incredibly rare lithium atoms would have to not only collide but do so with precisely the right orientation and energy to form a stable bond. It's a bit like hoping two specific grains of sand, scattered on opposite ends of a vast beach, will be washed together by the tide. In the near-perfect vacuum of the early cosmos, such an event would have been a true statistical miracle. Yet, theorists must consider it because its potential impact would be so profound. A molecule of Li2 would have been an even more efficient coolant than Li-H. Its more complex structure would have allowed it to radiate thermal energy away with incredible efficiency. If by some impossible chance a tiny pocket of the early universe had managed to form a cluster of Li2 molecules, it could have created an ultra-cold region, a bizarre super-chilled anomaly where gas could collapse and form structures at a rate completely unlike anything happening around it. It's the kind of theoretical outlier that, while almost certainly not a major player on the cosmic stage, forces scientists to refine their models and consider every conceivable pathway to complexity. These alternative lithium molecules represent the far edge of theoretical cosmology. We are almost certain we will never find direct evidence for Li2 in the primordial universe. Its expected abundance is simply too fantastically low. Li-H+ stands a slightly better, though still incredibly slim, chance. But we study them not because we expect to find them, but because the act of searching the parameter space of possibility teaches us something fundamental about the universe. By calculating the upper limits of their possible abundances, we place stringent constraints on our models of early chemistry and density. Their extreme rarity itself is a data point confirming just how pristine and sparse the early universe truly was. They are the ghost molecules of the cosmic dawn, theoretical specters that may never be seen, but whose very possibility helps us more clearly define the tangible reality of everything that came after. But what if our universe's entire timeline is just one chapter in a much grander story? To explore that, we must push beyond the standard Big Bang narrative and into the realm of alternative cosmologies like the pre-Big Bang and cyclic models. These ideas challenge the very notion of a singular beginning, proposing instead that our cosmos was born from the death of a previous one, or that it undergoes an endless cycle of expansion and contraction. This isn't just a new version of history, it completely reframes the mystery of the first molecules. If our universe had a predecessor, could the chemical foundations of everything we see have been laid down not at our beginning, but at the end of another cosmos entirely? Imagine the final moments of a previous universe in a cyclic model. It isn't ending in a hot, dense Big Crunch, but in a vast, cold, and incredibly diffuse state. Most matter has been consumed by black holes, which themselves have slowly evaporated over eons through Hawking radiation, but perhaps not everything is erased. Some theories suggest that in this near-empty void, certain ultra-stable structures could persist. These wouldn't be molecules as we know them, but something more exotic, perhaps cosmic strings, one-dimensional defects in space-time, or even stable clusters of particles bound by forces we don't yet understand. As the new universe begins its expansion from this state, these relics would be incorporated into the newborn fabric of our cosmos, not as intact molecules, but as seeds of order, subtle blueprints that could influence how the first particles arrange themselves. The influence wouldn't be direct, like finding a pre-made water molecule floating in the primordial soup. Instead, it could be far more subtle. These remnants from a prior cosmic cycle might have created tiny, localized variations in the density of the early universe, anomalies that served as the nucleation points for the first hydrogen clouds. They could have acted as pre-formed catalysts, surfaces upon which the first bonds could form with an efficiency that would otherwise be impossible in the pristine vacuum. In this view, the pattern of the cosmic web and the placement of the first molecular factories weren't random quantum fluctuations, but were subtly guided by the ghostly architecture of a universe that came before. The first handshake between two hydrogen atoms in our cosmos might have been a handshake across time, a final act of a forgotten universe making its mark on the new one. Of course, this remains one of the most speculative ideas in all of cosmology. There is no direct evidence for a pre-Big Bang universe, and the physics involved stretches our understanding to its absolute limits. Yet that is its power. It forces us to ask a deeper question about the nature of existence itself. Is chemistry, and by extension life, a unique event in a single universe, or could it be an eternal phenomenon, a story that has been told and retold across countless cosmic cycles? The search for an answer may lie not in looking for intact molecules, but in searching for impossible patterns in the cosmic microwave background, or for gravitational wave echoes that carry the signature of a time before time. It's a theory that challenges us to consider that our entire molecular history might be a legacy, an inheritance from a world we can never directly see, but whose faint imprint might still be written into the bonds of every atom around us. But to truly appreciate the efficiency of those first molecular bonds, we must consider a possibility so vast it redefines our place in the cosmos. This is the perspective offered by string theory, and specifically its concept of the landscape. String theory, in its quest to unite all fundamental forces, doesn't predict a single, unique universe with one set of rules. Instead, it suggests a staggering multiverse, a cosmic landscape of perhaps 10 to the 500 or more possible universes, each with its own unique set of physical laws and constants. In this breathtakingly vast ensemble, the strengths of forces and the masses of particles are not fixed, absolute truths. They are more like local ordinances, variables that can change from one cosmic domain to the next. The profound implication for our story is that the very laws of chemistry itself are not universal. They are contingent. The strength of the electromagnetic force that governs how atoms attract and repel, the precise mass of the electron, the specific energy levels within a hydrogen atom, all of these are dials that could be set to different values. In the endless variety of the string landscape, there are undoubtedly universes where the electromagnetic force is slightly stronger. In such a place, protons and electrons might bind together so tightly that atoms become miniature fortresses, utterly resistant to sharing electrons and forming molecules. The very concept of chemistry might be stillborn. Conversely, in a universe where the force is slightly weaker, atoms might be so indifferent to each other that they drift forever alone, unable to form even the simplest bond. No molecular hydrogen, no cooling, no stars, just a perpetual, sterile fog. Our universe, then, appears to be a remarkable exception. The constants here seem finely tuned or anthropically selected to allow for a rich and efficient chemistry. The mass of the electron and the strength of the electromagnetic force are set to a precise value that creates a Goldilocks zone for the hydrogen atom. It's stable but not too stable. It allows two atoms to approach each other, feel a mutual attraction through their electron clouds, and, with a little help from a third body or quantum tunneling, settle into a stable molecular bond. This isn't just a happy accident for life billions of years later. It was the critical first step that allowed the entire cosmic story to unfold. Without this specific setting of the constants, the primordial clouds of gas could never have cooled and collapsed. The darkness would never have been broken by starlight. This idea pushes our understanding from a simple narrative of how the first molecules formed to a deeper question of why they were able to form at all. The answer, from the string landscape perspective, is that we live in one of the very few universes where such formation was not just possible but efficient. In the endless cosmic lottery, we happen to inhabit a universe where the fundamental dials were set to chemistry-friendly. The formation of helium hydride and molecular hydrogen weren't just events, they were testaments to the specific local laws of this particular cosmic neighborhood. The fact that we are here to observe it is a consequence of that fact. This doesn't necessarily imply design, but it does suggest that our universe's capacity for complexity, beginning with that very first chemical handshake, is a rare and special property in a much wider and mostly barren multiversal landscape. To grasp this idea, we must venture into a realm where our everyday intuition completely fails, to a scale so small it is almost pure abstraction. This is the Planck scale, named for the physicist Max Planck, a domain where distances are measured in units of a trillionth of a trillionth of a trillionth of a meter. At this incomprehensibly tiny level, the universe does not behave like a smooth, continuous fabric. Instead, according to quantum mechanics, space-time itself is believed to be a seething, chaotic froth, often called quantum foam. Here, the concepts of here and there and now and then lose all meaning. Energy fluctuations are so violent that virtual particles, pairs of matter and antimatter, constantly pop into and out of existence, borrowing energy from the vacuum before annihilating each other and returning it, all within a time frame too brief to measure directly. It is a state of pure, undiluted potentiality, the fundamental churn from which all reality emerges. Now, rewind the cosmic clock to the first instance after the Big Bang. The entire universe was compressed into a volume smaller than a single atom, meaning that the entire cosmos was operating at the Planck scale. The quantum foam wasn't a microscopic curiosity, it was the entirety of existence. In this unimaginably dense and energetic environment, the quantum fluctuations weren't just tiny, isolated events, they were the dominant feature of reality. Space-time wasn't merely frothy, it was a rolling, boiling ocean of creation and destruction. The theory proposes that within this eternal storm, the fluctuations did more than just create virtual particles. They could have briefly and randomly generated the perfect, minuscule conditions for something more structured to occur. Imagine one of these fleeting fluctuations in the foam. For a duration measured in Planck time, an almost infinitely brief moment, a tiny region of this primordial chaos could have momentarily calmed. The energy density could have dipped just enough, and the geometry of spacetime within that pinpoint volume could have momentarily smoothed out, creating a temporary pocket of stability. In this transient oasis within the storm, the virtual particles bubbling up from the vacuum wouldn't have just been simple pairs of electrons and positrons. The conditions might have been right for more complex, short-lived clusters of particles to coalesce. These wouldn't be stable atoms or molecules as we know them, but perhaps the most primordial precursors, exotic, unstable hadronic molecules or dense knots of quarks and gluons that exhibited a fleeting, molecule-like coordination before being almost instantly swallowed back into the raging foam. Calling these entities molecules is a significant stretch of the definition, a poetic license to describe a state of matter for which we have no existing name. They would have been more like quantum echoes of molecules, transient patterns of order that flickered into and out of existence so quickly that they left no permanent mark on the universe. Yet their potential existence is profound. It suggests that the impulse toward complexity, the tendency for matter to seek out bonds and create structure, might be woven into the very fabric of spacetime at its most fundamental level. Even in the highest energy chaos of the beginning, the universe was, in fits and starts, experimenting with the very concepts that would later define it. This wasn't chemistry in any traditional sense. It was proto-chemistry, a ghostly rehearsal for the main event that would begin once the universe cooled and expanded enough for stable particles to exist. The challenge with this theory, like many dealing with the Planck epoch, is its profound resistance to any form of direct testing or observation. The energies and scales involved are so far beyond anything our particle colliders can achieve that it currently resides firmly in the realm of mathematical speculation. However, its value lies not in its provability, but in its power to expand our imagination. It forces us to consider that the journey from chaos to complexity may have begun not with the first stable hydrogen atom hundreds of thousands of years after the Big Bang, but in the very first moments of time itself within the quantum whirlwind of creation. It proposes that the seeds of the cosmic web of galaxies, stars, planets, and life might have been planted in the universe's very first frantic breaths as the quantum foam briefly and brilliantly dreamed of molecules. Now, let's consider a catalyst so elusive it can pass through light years of lead without a bump, yet so numerous that trillions pass through your body every second. We're talking about neutrinos, and a fascinating theory suggests this ghostly sea of particles flooding the early universe might have played a subtle but crucial role in guiding the first chemical handshakes. In the immediate aftermath of the Big Bang, the cosmos wasn't just a soup of protons and electrons. It was also inundated with an almost unimaginable number of neutrinos. For every proton or electron, there were about 1 billion of these barely their particles, creating a dense, invisible background that permeated every inch of the newborn universe. Their defining characteristic is their profound reluctance to interact with normal matter. They are the ultimate introverts of the particle world, governed only by the weak nuclear force and gravity. To them, the universe is almost entirely transparent. So how could such aloof spectators have possibly influenced the grand chemistry happening around them? The answer lies not in direct involvement, but in their collective gravitational influence and their role in the delicate energy balance of the plasma. While a single neutrino's gravity is vanishingly small, 1 billion of them in the same space as a single proton creates a different story altogether. This vast sea of neutrinos contributed to the overall gravitational potential of the universe, adding to the total mass-energy density that governed the rate of cosmic expansion. A universe expanding at a slightly different rate due to this neutrino background would have cooled at a different pace, directly affecting the precise moment when the temperature dropped enough for recombination, the formation of the first neutral atoms, to begin. If that window of opportunity for atom formation opened even a fraction of a second earlier or later, it could have changed the entire landscape for subsequent chemistry, altering densities and interaction rates at a critical juncture. Beyond their gravity, neutrinos may have influenced the early plasma through their minuscule but non-zero interactions. In the searing heat of the first seconds, neutrinos were actually coupled with the rest of the matter and radiation, constantly scattering off electrons and protons. This interaction helped shape the dynamics of the primordial soup, influencing how energy was distributed within it. As the universe expanded and neutrinos decoupled, flying freely through space, they continued to carry away a specific amount of energy and momentum from every region they left. This process effectively helped to smooth out the plasma, removing small-scale irregularities and subtly altering the distribution of matter on the very smallest scales. It's a bit like a vast cosmic filtration system, where the passage of countless neutrinos helped to fine-tune the environment, potentially creating slightly more uniform conditions in certain areas that were more conducive to the rare atomic collisions needed for bonding. Perhaps the most intriguing possibility involves a process known as neutrino heating in the outer layers of the very first collapsing gas clouds. While the vast majority of neutrinos would zip through a cloud of gas without a trace, a tiny, tiny fraction would interact with the free electrons and protons present. In a dense, collapsing protostellar cloud, even this infinitesimal interaction rate, multiplied by the staggering number of neutrinos, could have deposited a small but significant amount of energy into the gas. This isn't enough to heat the entire cloud, but it could create localized micro-heating events, tiny pockets of energy that stir the gas and increase the collision rate between atoms. In the cold, quiet depths of a primordial cloud, this gentle neutrino stirring could have been the nudge that pushed two hesitant hydrogen atoms just close enough for quantum tunneling to work its magic, catalyzing the formation of a molecule through the most indirect and subtle of means. It's a theory that reminds us that in the complex system of the early universe, even the most faintly interacting players could have had a part to write in the story of our origins. Perhaps the most mind-bending lens through which to view our molecular origins comes from a theory that challenges our most basic perception of reality itself, the holographic principle. This idea, born from the study of black holes and quantum gravity, proposes a radical notion that our seemingly three-dimensional universe with all its depth and volume might actually be a projection. It suggests that all the information needed to describe every star, every planet, and every one of us is actually encoded on a distant, two-dimensional surface, like a cosmic movie being projected from the edge of the observable universe. From this astonishing perspective, everything we experience, from the force of gravity to the passage of time, is not fundamental but emergent, a secondary effect rising out of a deeper, more fundamental layer of information. Apply this concept to the very first molecules and the implications are staggering. In the standard view, we trace their formation through a chain of cause and effect, particles cooling, atoms colliding, bonds forming through quantum tunneling. But the holographic principle invites us to consider a completely different narrative. What if molecular hydrogen didn't form because of those processes, but rather, those processes are simply how we, as characters within the projection, perceive a deeper computational event happening on the two-dimensional boundary of reality? The formation of that first bond might not be a chemical reaction at all in the fundamental sense. Instead, it could be the visible, three-dimensional manifestation of a change in the underlying information code, a bit flipping on the cosmic hard drive from 0 to 1 to signify that a molecule now exists in the simulation. This doesn't invalidate the physics we've explored, it just frames them as the language of the projection, the consistent rules that govern how the emergent reality behaves. The precise strength of the electromagnetic force, the exact mass of the electron, the specific probabilities of quantum tunneling, these aren't arbitrary constants. From the holographic view, they are the fundamental parameters of the cosmic code, the hardwired settings that determine how information translates into the illusion of physical law. The fact that these constants are so perfectly tuned to allow for chemistry is no longer a miraculous coincidence. It is a necessary feature of a universe whose code is rich enough to generate complexity. The first molecules were the moment the universe's program booted up its chemistry engine, a pivotal line of code executed in the cosmic dawn. This perspective also offers a fresh take on the role of entropy and information. A black hole entropy, which measures its information content, is proportional to the surface area of its event horizon, not its volume. The holographic principle extends this idea to the entire cosmos. The formation of the first molecules, which allowed gas to cool and collapse into the first stars, was a massive local decrease in entropy. But on the boundary surface, this event might have been represented as a massive increase in information complexity, a new and more intricate pattern being written into the cosmic code. The collapse of a gas cloud into a star isn't just a gravitational event. It's an information processing event where the simple, repetitive data of a uniform cloud is transformed into the highly ordered, complex data structure of a stellar system. Ultimately, the holographic principle transforms the first molecules from simple chemical curiosities into something far more profound. They become the emergent signatures of reality itself booting up. They are the proof that the cosmic code was not only running but was sophisticated enough to generate stable structures that could interact, combine, and build towards ever greater complexity. While this remains a deeply theoretical framework, it provides a powerful, unifying vision. It suggests that the quest to understand the first molecules and the quest to understand the most fundamental nature of reality are not separate journeys, but one and the same, a search for the source code of the cosmos, written in the language of bonds, spins, and quantum information, with every molecule that has ever existed serving as a living testament to its elegant and breathtaking logic. Now, let's stretch the boundaries of cosmology to its absolute limit with a theory that questions the very independence of our universe's origins. This is the multiverse chemical seeding theory, a concept that proposes our cosmic story might not be a wholly original production. Imagine our universe not as a solitary island, but as one of countless islands in a vast multiversal archipelago. In such a reality, the empty space between universes might not be a perfect, impenetrable void. The laws of physics as we know them could break down in this meta-space, potentially allowing for the most minuscule of leaks, a trickle of particles, a whisper of a fundamental field, or even pure information bleeding from one cosmic domain into another. The mechanism for this crossover is purely speculative, drawn from the edges of theoretical physics. Some models of string theory suggest these sibling universes could be separated by membranes or branes that exist in higher dimensional space. Under the right conditions, these branes could vibrate or even briefly collide. During such a monumental event, it's conceivable that material could be exchanged. We're not talking about asteroids or comets drifting through a cosmic rift. The transfer would be far more subtle, perhaps a shower of exotic particles that don't exist in our universe's stable form, or a slight, localized alteration to the value of a fundamental field, like the Higgs field, which gives particles their mass. Even a burst of quantum information, a pattern of order from a foreign reality, could theoretically imprint itself onto the chaotic energy of our newborn cosmos. The impact of such a leak wouldn't need to be dramatic to be profound. it wouldn't require a truckload of pre-made water molecules tumbling into the primordial soup. The influence could be incredibly subtle yet transformative. Imagine a single, stable, massive particle from a universe with different physical constants drifting into our own. This exotic object would act as a ready-made catalyst, providing a surface for hydrogen atoms to meet and bond with an efficiency far surpassing the slow three-body collisions. Its mere presence could have jump-started molecular production in a localized region, creating the first fertile island of chemistry in an otherwise barren expanse. Alternatively, a slight tweak to a fundamental force in a specific patch of space could have lowered the energy barrier for quantum tunneling, making the formation of those first hydrogen bonds not a rare quantum fluke but a commonplace event. A universe that was struggling to light its first chemical fires might have received a gift of metaphorical matches from a neighbor. This idea fundamentally recontextualizes the anthropic principle we discussed earlier. If our universe's physical constants seem perfectly fine-tuned for chemistry and life, it might not be because we won a cosmic lottery. It could be because we are the beneficiaries of a legacy. A neighboring universe, perhaps older or with different underlying laws, could have served as a template or a donor, seeding our cosmos with the slight nudge it needed to embark on its journey toward complexity. Our universe might not be fine-tuned. It might be fine-tuned up, adjusted by an external influence we can scarcely imagine. The first molecules, then, would not be solely ours. They would be hybrid creations, their existence made possible by a whisper of physics from beyond our dimensional horizon. While this remains one of the most untestable ideas in all of science, it challenges our deepest assumptions about isolation and origin, suggesting that the handshake between two hydrogen atoms might have been guided by a hand from another world entirely. Finally, we arrive at a theory that is less a scientific hypothesis and more a profound philosophical proposition, one that places consciousness itself at the very heart of cosmic creation. This is the consciousness collapse hypothesis, and it suggests that the quantum potentialities of the early universe required an observer to crystallize into the definite reality we now inhabit, including the formation of those first crucial molecules. To understand this radical idea, we must first revisit a core principle of quantum mechanics, the wave function. Before a quantum system is measured, it doesn't exist in a single defined state. Instead, it exists in a haze of overlapping possibilities, a superposition of all potential outcomes. An electron isn't here or there, it is smeared out in a cloud of probability. It is only upon observation, upon measurement, that this wave function is said to collapse, forcing the system to choose a single, concrete reality from the infinite menu of options. In the early universe, this quantum weirdness wasn't confined to the microscopic realm. The entire cosmos was a quantum system. Every particle, every potential bond between hydrogen atoms existed in a state of flux. The formation of the first molecular hydrogen bond wasn't a foregone conclusion. It was one probabilistic outcome among countless others. The conventional Copenhagen interpretation of quantum mechanics states that this collapse is triggered by any interaction with a macroscopic measuring device. It's a physical process. But the consciousness collapse hypothesis, most famously associated with the work of physicist John von Neumann and later Eugene Wigner, pushes this idea to its extreme limit. It proposes that measurement devices are simply complex collections of particles themselves, also governed by quantum rules. The only thing that can truly collapse a wave function, the only thing that isn't part of the quantum soup, is a conscious mind. Observation requires an observer. Apply this to the cosmic dawn, and the implications are staggering. For billions of years, the universe expanded in a state of pure potential. The wave functions of every hydrogen atom remained uncollapsed. The helium hydride ion both existed and did not exist. The entire cosmos was in a superposition of states, a blur of might-have-beens waiting for something to look at it. Then, according to this view, consciousness emerged. Perhaps it was the first primitive awareness within the first living organism on some distant world, billions of years after the Big Bang. In that moment, by the mere act of perception, that conscious entity did not just observe the universe, it retrospectively created its entire history. By looking out at the stars, it collapsed the universal wave function all the way back to the beginning, freezing a single timeline into existence, one that included the specific sequence of quantum events that led to the molecules that cooled the gas that formed the stars that forged the elements that made life possible. In this view, the first molecules formed because a conscious being eventually observed them, a bizarre inversion of cause and effect where the future literally defines the past. This idea is unsurprisingly met with intense skepticism within the physics community. It ventures from the realm of testable science into pure metaphysics. Critics argue it is solipsistic, placing an impossible burden on consciousness and making science itself subjective. They point to decoherence theory as a more plausible explanation, where interactions with the environment cause quantum systems to effectively behave classically without the need for a conscious observer. Yet, the hypothesis endures because it tackles the hard problem of measurement in quantum mechanics head-on. It forces us to confront the deeply strange relationship between the world we perceive and the underlying quantum reality. Whether one accepts it or not, it serves as a powerful reminder that our universe's story is not just a tale of particles and forces, but may be inextricably linked to the very phenomenon of awareness, suggesting that the cosmos became real because it was eventually seen, and that every atom, in some profound sense, was waiting for you. From the first tentative bonds of hydrogen molecules born in the cold, empty dark to the fleeting existence of helium hydride in the searing heat of creation, this journey has taken us from the bedrock of established science to the very edge of cosmic speculation. We have witnessed how these simple acts of atomic handshake set the entire universe in motion, cooling the primordial gas and igniting the fires of the first stars. We have ventured into the shadows to see dark matter's potential role as a hidden catalyst, and plunged into the violent hearts of primordial black holes where chemistry was forged in gravitational fury. We have even dared to look beyond to the possibility that our universe's finely tuned constants are a rare gift in a vast multiversal landscape, or that the very act of observation might have written this history in retrospect. Each of these theories, from the rigorously tested to the wildly imaginative, is a vital piece in the grandest puzzle of all, our own origin story. To unravel the mystery of the first molecules is to trace our cosmic ancestry back to the very beginning. The hydrogen in the water you drink, the carbon in your cells, the oxygen you breathe, every atom in your body beyond the simplest hydrogen was forged in the heart of a star that could only have existed because of those first fragile molecules. We are not just living in the universe, we are a product of its earliest chemistry, the universe itself become conscious and looking back to understand its birth. The search is far from over. Every new tool, like the James Webb Space Telescope, peels back another layer of time, offering us a clearer view of that cosmic dawn. What will it find next? Perhaps the definitive spectral signature of helium hydride in the most ancient galaxy, or evidence of population 3 stars that confirm our models of early cooling. Maybe it will discover something entirely unexpected that forces us to rewrite the entire first chapter. The conversation continues with all of you. Which of these 30 theories resonates most with your view of the cosmos? Does the quantum magic of tunneling feel more compelling than the cosmic choreography of gravitational waves? Do you think the answer lies in the pristine laws of physics we know, or in the wild frontiers of multiverses and consciousness? Share your thoughts and your own speculations in the comments below. I read every single one. If you've enjoyed this deep dive into the foundations of reality, make sure to subscribe and hit the bell so you don't miss our next exploration into the mysteries of space, time,